Hello, everyone, and welcome to our SETI Live. I'm Sarah Jennings with Frontier Development Lab. Frontier Development Lab is an applied artificial intelligence research accelerator, and we bring folks from around the world in machine learning and space science, and we pair them together to work on interesting challenges with NASA and our private sector partners. So we are in week 6 of FDL, and I am here today with another one of our amazing FDL teams. This team is the Solar Wind team. Some of our previous SETI lives, we've had a lot of conversation about the most interesting thing that they learned from FDL was actually that there is space weather, and that this is kind of an interesting new concept that they hadn't thought about. So really exciting to be talking with this team today. So I'm joined with Amanda, Nathan, Mavis, Marcella, and Sadishna. So thank you guys so much for coming today. And to kick us off, I'd really love to hear a little bit more about the challenge that you're working on and why it is important. So Amanda?
Yeah, absolutely. So first, I think it's probably very important to understand what exactly solar wind is. So if you give me just a moment, I want to share an animation with you. Let me know if you see it, because I know it sometimes takes a moment to load. I'm assuming silence means it's visible. So I'll go ahead and start. So if you take a look at the animation, you can see our solar system, and you'll see our sun in the middle, and every star has an extended atmosphere that radiates outwards into space. And this atmosphere is made of charged particles or plasma that we call the solar wind. There are two types of solar wind, fast and slow. And of course, based on the name, you'll assume correctly that it's partially based on the velocity or speed of the solar wind, but it's also based on its source. So for fast solar wind, we have a pretty good understanding of the source, and this fast solar wind travels upwards of 750 kilometers per second, or almost 200 million miles an hour. But slow solar wind, which is actually the focus of our project, isn't very well understood. And so because the Earth is constantly bathed in slow solar wind, even though we're largely protected by the Earth's magnetosphere, which is generated by the Earth's magnetic field, it can still interact or interfere with some of our assets in space, such as communications, GPS, long-term space exploration, and our astronauts, such as the ones that are living on the International Space Station. So understanding the source and the structure of solar wind is very important. And when I refer to the structure of solar wind, I can get my slides to change. There we go. We're taking kind of a zoomed in look at the sun here. The sun's in the middle, and you can see the solar wind kind of radiating outwards. Hopefully you can see my mouse moving around, and you can see that there's a lot of really nice structure here. So a part of our project is to really understand these structures, which will in turn help us understand kind of the source of the solar wind overall. And that's our challenge in a nutshell, really.
That was a fabulous explanation, really, really wonderful, and really drives home the importance of space weather. And even if we don't really think about it, how much it really does impact us and our entire solar system and beyond. So thank you very much for introducing the challenge. I would really like to know a little bit more about what you guys are working on as far as cataloging the work, and why a catalog of this doesn't already exist. So Nathan, I'm hoping you can answer that question.
Yeah, thanks, Sarah. Good question. So let me pull up my slide here. All right, so I'll do a little pause here. So hopefully it has time to show up on everyone else's screen. All right, so as Amanda was just talking about, there's lots of structure in the solar wind. And not only is there lots of structure, but there's lots of different types of structure that show up in the solar wind. We have things that span timescales that are on the order of days, and these are called interplanetary coronal mass ejections. And so these are some of the largest structures that show up in the solar wind. And these are the ones that are sort of the most dangerous for humans, up in low Earth orbit, and can really affect not only satellites in low Earth orbit, but also power systems down on the ground. And these typically order in the number of tens to say 50s per year at Earth. So Earth is located 1 AU from the sun. So 1 AU is it's an astronomical unit, and it's 93 million miles. And it's sort of the average distance that the Earth is from the sun throughout the course of the year. And so these are, an example of one type of structure, but you can see here there's many more. So we have small scale magnetic flux ropes that have time scales that span from minutes to hours. And there's, thousands of these that show up per year. And we have even, other small scale structures that are different, that are called interplanetary magnetic field enhancements that span time scales from minutes to hours as well, but occur less frequently throughout the year. And then finally, we have these magnetic discontinuities, which are sort of the smallest structures that show up in the solar wind. And there's just tons of these that show up every year. And they're very difficult to go through and manually verify, right? So you imagine there's 10,000s of these that show up per year, tens of thousands of them, and there's many years worth of data. And so what we want to do is build catalogs for these very hard and pesky objects and structures in the solar wind, right? So you can imagine for these large scale structures like interplanetary coronal mass ejections, it's pretty easy to go look at, some data and say, okay, yes, this first one out of our list of 20 is an ICME. Let's go to the next one, right? You can envision somebody doing that. But once things start to spin up to on the order of thousands, it becomes very difficult. And it's very labor intensive, and it's very time consuming for researchers who want to understand what drives these structures from a first principles physics standpoint. And so what we would like to do is take artificial intelligence and apply it to the solar wind so that we can build these catalogs of these really small scale structures with minimal bias. And by removing and minimizing the bias in the structures, hopefully we can provide these researchers with catalogs that are faithful representations of the objects that they should contain. And it'll allow people to really have a test bed for improving theories and furthering our understanding of the solar wind.
Thanks, Nathan. That was a really good overview of the structures and why you need this type of catalog. I was wondering if I could get a little bit more of an explanation about the data that you guys are using and where it comes from. Sadishna, are you able to share a little bit more about the data?
Yes, absolutely. Absolutely, Sarah. I'll pull up my screen here. So we are looking at data from two different instruments, two different spacecrafts, and some of you might, or probably all of you know that there are multiple different spacecrafts that are actually monitoring and observing the sun as we speak. And we're going to focus on just two of them. And the first one that we're interested in is the Parker Solar Probe, which is an instrument that was launched in 2018. It's one of the newest spacecraft that was launched, and we have data from around 3 years worth of data. Another instrument that we're also interested in is actually the wind data, which was launched in 1994, and we have at least 20 to 25 years worth of data, and we are going to focus on only 15 years worth of data. And there's a reason why we are actually monitoring these two instruments, why we are using data from these two specific instruments. As Amanda mentioned, that the solar wind is radiating outwards, and as it is doing so, you can imagine that there are different structures in the solar wind. So whatever structure we have closer to the sun is probably not going to be very similar to the ones that we have near Earth. So if we have instruments at different locations on the solar system, we should be able to get a very good understanding of what's happening with this wind of the sun. So I'm just going to show you the orbit of PSP, or Parker Solar Probe. So it's a very unique instrument because this spacecraft is orbiting the sun, and at some stage it's going to dive straight into it. And what you see here are the spirals showing the orbit of the Parker Solar Probe, and the green dot, if you can see it, if my cursor is pointing and you can see there, this is exactly where Parker Solar Probe was today at 1800 UTC. So this is where the instrument is right now. And the green orbits show the orbits that the PSP has already made, and the red ones show where it will be in the future. And as you can see, as it's moving from the Earth towards the sun, it's covering a very large distance, 1 AU more or less. And that means that we'll be able to understand what's happening to the solar wind as it's moving and as it's moving radially outwards. And just to give some context here about wind is situated here. Wind is actually very close to Earth. So as you can see, by comparing the data from these two different instruments, we'll be obtaining a wealth of information about the wind, the solar wind. And just to give you a glimpse of what kind of data actually we're looking at, we are looking at the magnetic field data specifically, and this is what we would call a time series of magnetic field over time. It shows how the magnetic field of the wind is varying with time. And at the bottom, you also see the velocity as well. And as Amanda pointed out, that the fast and the slow wind is differentiated based on the velocity. And what you're seeing here is more or less the slow wind velocity. So these are the instruments that we are investigating, and this kind of data is what we are playing around with at the moment.
Awesome. Thank you so much for that overview. So now I feel like we've got a really good idea of both the challenge, the cataloging, the data that you guys are using. And so in a second, we'll dive in more on the techniques that you're using. But just wanted to do a quick shout out first to our audience members that are coming in from all over the world. It looks like we've got Louisiana, Greece, London, Brazil, Indiana, Colorado, Ireland, the UK. Virginia. So thank you all for joining us today. And if you do have any questions, we already see some questions coming in, please send them to us and we will have a little bit of time at the end for some audience questions. So with that, let's shift back. And if you can describe a little bit about the techniques that you're using for this particular challenge. And so I'll pass it over to Marcella.
Oh, thank you, Sarah. So mainly we are applying artificial intelligence techniques. So it means that we teach the computer how to process and analyze all this data we have. So we take advantage of all this power of this computer tools instead of doing it manually, like Nathan said. So then we can save lots of efforts and also save time, and we don't need too much expertise because we are teaching the computer to do this for us. And given this fact, I will share my screen just to show such tools, an example of a tool that we are using. So okay, now you can see my screen. So here, like Sudeshna told you, we are now analyze the magnetic field from the solar wind. So our data set is a huge amount of data that have been collected from both instruments. In this figure on the left side, you can see only 5 minutes. So then you can imagine how much data we have, since we have been captured over years, during over years. And then what we can do with this data is using the computer and such tools to transform this data into images, for instance. And then the computer is able to learn from this image and then to classify these images, trying to find some events and some objects in the solar wind that can really impact the weather on Earth. So basically, we take advantage of the classification created by the computer itself, because we teach the computer and the computer learns how to do that. And then we don't need to do it manually. So we can save lots of efforts, and then we can use it as a classification, for instance, in this case.
Great. Thank you so much. That was a great overview. And now I think is one of the most exciting parts. I would really like to know what initial results your team has. We're in week 6, so you still have a couple of weeks left, but I would love to share with the audience anything that you guys are able to share.
Should I go ahead and present for ISACs, and then Marcella can take the listen? Okay, cool. So I'm going to go ahead and share my screen. So can you see this? All good? Awesome. Okay. So here's some results that we just got actually last week. So what you're looking at here are the same magnetic curves that we have been talking about, that Sudeshna showed earlier from PSP and the WIND spacecraft. And so what we're essentially doing here is we're trying to identify similar structures in the solar wind magnetic field. So if you were to look in this area on this plot on the right-hand side, you can see that there's these straight lines in the magnetic field. And these are the kinds of structures that Nathan was talking about earlier that we're searching for and that we want to catalog for the heliophysics community. So here, if you look at our legend, you can see that there's different timestamps, different date timestamps. So essentially what we're doing is we're grouping together all these similar structures in our entire data set. So we have like 315,000 plus measurements from the past 3 years from the PSP. And by being able to group together these similar structures, we can actually be able to get a better idea of just how solar wind evolves throughout time. And back to the plot on the left, you can see that essentially what we've done is for all these magnetic curves on the right-hand side, we've compressed them. So basically we're taking all the very important details that we want. We don't want to look at the noise or any trends that are characteristic of solar wind. We just want, just the meat. So what we've done is we've taken that meat of all the magnetic curves, we have brought them together. That's what our algorithm does. It brings together the similar features, and then finally allows us to sort them into these different groups that we can then categorize and save for later analysis. And now I'll pass it back to Marcella, who's going to talk about our other method.
So, and in our other method, like I previously mentioned it before, we not only do the clustering, so we don't just group all the similarities that we have from our data, but also we try to classify. So we take the wind data that we have storage, and then basically what we do is to try to find some in a new data that we are receiving, we try to find some new information that it will tell us if we have an event that is happening in the solar wind or not. So the computer can do this for us and then can classify an event that is occurring. And the other side, because PSP is a very new instrument and we just have data since 2018, we don't have label data. So it means that we don't know in exactly parts of the time we have some events or objects, and then what we can do is just to group the similarities that we have. So basically we just chunk the time series, the time that we have, and then we just cluster them all based on the similarities that we have. So are the both techniques that we are applying, and they are called as supervised and unsupervised learning, because one, we know the data and the label, and the other we don't know. We just can do what we just can do is just to cluster them all and just to try to see if we can find some similarities, and then we can play with this, and then after we can create our catalog, and in this catalog we can just present it to the specialists, to the physics, and then they will tell us, okay, this is really important because now we can classify our events and then our objects that we have in the solar wind structures. And then this is basically what we need to understand the weather, the impact on the weather that we have here on Earth. So this is why this is important to us to do this kind of, to understand the behavior of the solar wind.
Awesome. Thank you so much. And thanks for sharing some of the initial results. And I'm looking forward to seeing what you guys are able to show us at the showcase and beyond. So really exciting work. And now I'd like to shift gears a little bit and ask all of you a couple of questions before we take some from the audience. We also have some other viewers tuning in. We have Bulgaria and Iceland and Florida and Michigan. So welcome for joining us. So the next question is, why are you specifically interested in this challenge? And so I'm just going to call on each of you to kind of share what brought you here, why you're interested in the work that you're doing this summer. So we'll start with Amanda.
Yeah, thanks. So I don't think it was mentioned before, but Frontier Development Lab projects up until this summer usually were comprised of like postdocs and folks in industry working on these problems. And myself and Mavis are actually the very first undergraduate students to work in this program. And so for me specifically, research really didn't feel like a viable option for me. And a lot of that, is rooted in a lot of self-doubt and imposter syndrome. But everything for me about space is interesting. So it was hard with little direction or opportunity to narrow down a focus. And so when I got a call from our team lead, who's not here today, I really just had to take a leap of faith, not only in the team that I was going to be a part of, but in myself, knowing that I would be able to learn and be a contributing member to the team. And I really feel like I have. In fact, as a result of this opportunity, I will have another opportunity to continue doing research with my university for another fellowship, which I'm really excited about. So the process of participating in research and growing both technically and personally has really been a life-changing opportunity for me. And as far as this particular challenge, kind of just understanding the universe in which we live is fascinating. Slow solar wind, as we understand it today, may not have a huge impact on our way of life, but of course, just kind of like understanding weather as a whole, even when it's beautiful and sunny, is really just going to help us kind of exist in the world that we live in, and that's what really interests me about this challenge.
Awesome. Thank you so much for sharing, Amanda. And we're really excited that you're here this summer. So thank you. And Nathan, we'll go to you next.
Oh man, how do I follow up that answer? That was phenomenal. So jealous. No, so for me, this is the exact sort of stuff that I've always wanted to do, but never really knew existed for space physics. And so when I discovered the Frontier Development Lab and was like, I had read the project description, it sounded like I had written it, how closely it was aligned with what I wanted to do. And it was like my first experience of anything FDL. And so like, it's so applicable for everything that I will be doing throughout my career. So I'm a first-year PhD student. And by developing these tools, I really think we're going to help accelerate science and extracting meaning from the solar wind. And so that is what I'm really interested in.
Awesome. Great answer, Nathan. Thank you so much. And we'll go next down the line to Sajishna.
Okay, so yeah, so I'm a postdoc. So and I'm actually study stars, which are very similar to our sun. So I'm interested in learning how the host star impacts the atmosphere and a planet, basically. So now we have so many exoplanets detected, but the next step for us would be to understand whether any of these exoplanets are habitable. So what I study is how does the sun or how does the star impact the habitability of these exoplanets? And although I started off my PhD doing data analysis and doing some little bit of modeling and whatnot, and last year I really got into machine learning and AI. So for me, I felt like, okay, if we want to know about anything about exoplanets, then we need to first understand our own planet. We need to understand about our own Earth. We need to understand about our own sun. And when it comes to solar physics, there's so much of data that's out there. You're basically drowning with information. And machine learning and AI is one of the very best ways of actually applying these techniques and then getting something out of it. So this is a perfect combination of AI, science, and I feel like I'm in the sweet spot and I'm really enjoying my time with all these wonderful people working together. Yeah.
That's awesome. Thank you. And definitely in the right spot. And we'll next go to Mavis.
Yeah, so similarly to Amanda, just, you're an undergraduate and you hear about this program that's comprised of basically just postdocs and graduate students. You think to yourself, oh, well, how am I supposed to, what will I be able to contribute to this? But something that our team lead and all of our teammates have really emphasized was like the value of learning. And growing up, I really have always enjoyed learning. But during this summer, I've come to learn things more about machine learning that I didn't know about before. And I have to say, I haven't always been very confident about coding. I have a very bad history with coding. But yeah, back in high school, it seems simple. Then entering college, you start learning about all these other different kinds of data structures, and you realize, oh wow, there's a lot more to programming than I thought prior. But throughout the summer, we've really been taking advantage of like the object-oriented aspect of Python in classes, and also just different machine learning mechanisms like clustering. And I remember at the beginning of the program, I was just consulting a bunch of my professors from my college asking, hey, what does this method do? What is this kind of program thing in machine learning? I have absolutely no idea what this is. And I was surprised to learn that a lot of them actually weren't too familiar with the methods that we were using. And that's because in FDL, what we're doing is we're basically creating new infrastructure for programming. Like everything is literally like taken from scratch. These are things that people have not yet explored. And that's why FDL has taken on these challenges. And I think that's one of the things that really did attract me about FDL, just the fact that we're doing new research that people have not yet touched. And we're seeing this for the first time. Like we're the ones first laying our eyes on this. It's like finding that treasure, But aside from that, I go to a college that's just undergraduate, so they don't work. We still get to do research with our profs, but we don't work with graduate students or postdocs. So I've been told by professors from other universities, like, hey, you're missing out. You don't really, you're not interacting with the cool kids. So now I get to say, hey, but you know what? I did interact with the cool kids. I got to spend one very awesome summer with a bunch of very cool kids. Thank you very much. But yeah, that's my story.
That's awesome. Thank you, Mavis. And yeah, truly, like we do work on the cutting edge stuff. We're able to work on new research that hasn't been done before. So that's a really exciting piece of what we get to do at FDL. So thank you. And now we'll go to Marcella.
Thank you, Sarah. Well, I think this is because I basically always wanted to be an astronaut. So this is as close as I can be of it. So for me, FDL is a great opportunity to learn about the space, and I am really passionate about it. So this is really exciting because now I can really contribute somehow to the science, and also I can share technology, and I can also learn from the other people and from other areas. So this is something really new for me, because I am learning a lot. And then this is why I think it's very important, because each one can contribute. And then, well, since I have been giving classes of artificial intelligence, I have never seen things like this before, because everyone can help each other. And then this is why FDL is really important for me, and this is why I am here. So basically to learn and to know all I can do about space and this kind of things.
That's awesome. Thank you. And now I'm just curious, on this call, can you raise your hand if you are also interested in becoming an astronaut? Cool. A few people. Sounds good. Seems good. I'm personally more interested in mission control, but I'm really excited that you guys are interested in becoming astronauts, and that the work that we're doing is really beneficial to humanity on the whole. So thank you all. And now I'd also like to ask you guys another question. We've learned a lot during FDL, so I want to know what the most interesting thing that you have learned over the past 6 weeks is. So I'm going to go in a different order this time, and I'm going to kick off with Sajishna.
Oh, where should I start? So this, I have to say, I knew that coming into FDL, there were loads of things that I wouldn't know, and there are loads of things that I would learn, as Marcella said, which is happening. But I think one thing that I probably didn't really think about, and I found it very fascinating, was that you think, okay, I have worked on these kind of topics before, so, I have coded before and whatnot, so I know that this probably won't work, and this is probably the right way of doing things and whatnot. And you have your own mindset and you go into it. And then you are working in a team, and then someone says, have you thought about it this way? And it's like, oh my God, how am I so stupid? I have never thought about this before. So it's so fun to actually explore these things together that you would never ever think of it, but then someone just points out and someone says, oh, let's do it this way. And it's so much fun. So I was a bit stressed when I first started FDL, thinking, oh my God, I have to share codes with other people, and I'm not very good at programming. I'm a terrible coder, so I don't want to share my screen with other people. But during this whole experience, you learn so much about yourself as well, and it's such a good learning experience. So every single day is fun. So yeah, it's great. I'm really enjoying myself. Probably a bit too much. So yeah.
I don't think you can enjoy yourself too much during the FDL program. It's super good to hear. And yeah, it's amazing to have so many different perspectives to be tackling a particular problem. So that's awesome. And we'll go next to Nathan.
Yeah, this is so tough. I feel like I've learned so many just like interesting things, and it again all comes down to having, you know, a bunch of people in a room that all come from different backgrounds, that all have different expertise. And I think the thing that really sort of like blew me away is learning about all the different ways that people are manipulating time series data to put it into a different structure that is like compatible with machine learning. So for example, turning regular time series data into an image. I didn't even know that was a thing until I came to FDL. And so like I saw that and I like made the first image and I was like, oh my God, this is crazy. Like we can actually do this. And then you just start feeding those into a computer and then it like learns from that image what the time series is. And it's just everything is very fascinating. So it's hard to like really single out one interesting thing. But if I had to, I think it would be just manipulating time series into like different representations.
That's definitely a great one. Thank you, Nathan. And we'll go to Mavis next.
I guess there's two different things I've learned. For the first thing, quite similarly to Nathan, just being able to manipulate time series data. So for the method I was showing earlier, that's called ISACs. And hardly anyone knows about ISACs. ISACs is just this completely alien thing that we spent like nearly an entire week trying to figure out because there were no open resources online except for maybe one source, and it was in French. So we had to Google Translate the page. It was honestly, looking back on it, it was kind of hilarious. But just realizing how computers really they're really highly powered. Like we know that they're highly powered, but once you start machine learning, you realize the true power of computers, like being able to compress data and take all these complex details, somehow simplify them, and still be able to group together similar structures. Like, how does it do that? And woo! So there's a lot of math involved too, and just I feel this program has really, it's motivated me to take more math classes. So I, as a physics major, I am completely done with all of my math prerequisites, but I would love to take more math classes because of this. And secondly, I'd say that this program has definitely reshaped my perspective of just working with like postdocs or like in academia and so forth, because I didn't have the best experience myself when I first did research a couple summers ago. The environment was kind of toxic, and there was just all this hype about like Ivy Leagues and like, you know, just not really, there was no value placed on practical work. It was more so, how complicated is this work? Can you explain it? And can you understand it? If you can, then that means that you're like a big boss or something. And so then I felt very pressured in that environment to perform like much higher than my own expectations. And I found myself always stressing out. And coming here to FDL, just everyone is very understanding. Everyone's actually patient, and they take the time to explain things to you. And when you're confused, you know, they don't look down on you. They say, hey, I've been in that spot before. Like, I've been in undergrad before. I've started out in industry before. I know how you feel, and I am going to help you out because you don't have to feel that way. That's why we're here. And so I've come to learn that, yeah, you know, that I'm not supposed to fear my coworkers or like anyone else who's higher in academia. Like, they can be mentors, and mentors do exist. Yeah.
That's great. Thank you so much, Mavis. And next we'll go to Marcella.
Well, I think the most special thing I have learned from FDL is how to work in our group. So basically, because first we really knows what is the reason that we are here, because we share our knowledge and then we can open our minds. So we are pushed by themselves inside the group to open it. And this is really amazing and exciting, because now we really understand that we can do it, and we can do it more because we are together, not because we are giving the best of ourselves, but because we are giving the best of our entire team. And then we have pushed it to only a specific goal, but the goal is not to deliver something or just to be fast, but learning. This is the amazing part of FDL. And this is what I have been learning, that the most important is that everyone here has to be on the same page. Everyone here has to learn at the same level, because we are the team. And the other thing that I have learned is about our voices. So our team leader, he always say that our voices has too much power. And when we say about it, when we share about what we are thinking, this is absolutely exciting and amazing for each one of us, because then we can explicitly say what we are thinking, and we don't need to worry about what the others will think, because we are a team. So we are very comfortable to do that. Besides all the machine learning involved, of course.
Yeah, that's a great response. And we definitely believe that the research that we do is a team sport. So that is a great explanation of that in practice. So thank you. And we'll go to Amanda.
Yeah, so as far as on the technical side, pretty much everything I've learned is fascinating, because I came into this program with pretty much zero knowledge of everything that we're covering, everything about the sun that we've been talking about, everything with coding and machine learning. I had like a little bit of coding experience before I started, but really not at the level now, just after like 6 to 8 weeks, which has been really, really great. And I hope that it shows just how much I've been able to learn. I hope it sounded like I was speaking with some level of competency when I opened everything up, but that was just what I've learned over the course of the summer. Again, I had no background on any of that before I started. But the other thing that's been really eye-opening to me, to piggyback off of Mavis's second point, is really just the interaction that I've had with everybody on this team. And even in the FDL as a whole, everyone who's a postdoc or in grad school. I think, being also a first generation college student, I didn't have access to people like that. And I think I, for a long time, held a stereotype in my head of people who hold PhDs kind of on a pedestal, inaccessible, kind of like that bad experience that Mavis was talking about. And interacting with the people through the FDL, we've been able to kind of create a space in which we're all vulnerable, which we all have our own insecurities. And of course, with the guidance of our team leads and obviously the amazing attitudes of everyone on the team, we've created a space where we're really comfortable with this, and we're all growing and we're all learning, even though we're all at really different levels in our education and in our careers. And so these interactions have made me feel like research, or even like a graduate school education, is possible for me. And if I may, I actually first went to college over 10 years ago and basically flunked out of aerospace engineering. And now, like, I'm back interacting with all of these amazing people about to graduate with a degree in engineering, and even going to grad school. And I think without these experiences, without talking to people and kind of feeling like that experience is possible for me, I might, have never done it. So I hope anyone watching who might be in a similar experience that might feel like this kind of research isn't accessible, or maybe you don't have what it takes, I encourage you to kind of take a leap of faith and kind of pursue the things that are really interesting to you. It might take 10 years for the fact to do it, but you can do it anytime. It doesn't matter how old you are. So yeah, sorry, that's really long and probably more deep than you were expecting, but I think that's definitely my biggest takeaway from this program, for sure.
I don't know, that's really, really great and very inspiring. Thank you so much, Amanda. And I think we are coming up to our time. And I know you guys are very busy in week 6. So I'm going to go ahead and let you guys go. And I just wanted to say thank you again to our solar wind team. You guys have done an amazing job. And I am really looking forward to seeing the work that you guys do in the coming weeks. Thank you to our audience. We'll be back again with some more SETI Lives with the FDL teams. So appreciate everybody taking the time and just wanted to say thank you.